Welcome to AI Paperslop. If you're an AI researcher or, an ML engineer building generative models, you absolutely know the agony of alignment right now.
Oh, yeah. It is brutal.
It really is. I mean, generative AI normally requires dozens of steps just to make a single image or video. You're constantly recalculating that instantaneous velocity over and over.
And that's just for generation.
Right. And if you want to actually align these models with reinforcement learning using something like GRPO, you have to unroll that entire reverse process.
Which is just a nightmare for compute.
Exactly. You're sitting there calculating per step likelihoods, watching your GPUs just absolutely scream, and constantly dodging out of memory errors.
Yeah, the errors are real.
So real. But today we're looking at a July 2026 paper from Tencent Hunyuan and HKUs. It's called MeanFlowNFT, bringing forward process RL to average velocity generators. And the TLDR here is just crazy.
It really is a massive shift.
Yeah, so basically the authors found a mathematical bridge. They connected fast, few-step, average velocity generators, which we know as MeanFlow, with this highly efficient, likelihood-free forward process RL called diffusion NFT.
And the practical result of putting those two things together is just staggering.
I mean, they built a 4-step video generator that outright beats a 50-step RL-tuned diffusion model.
Wait, 4 steps beating 50?
Yeah. It achieved a V-bench score of 84.33 on 1.2.1, and the 50-step model, it only got 82.57.
That is, just to emphasize exactly why this should matter to you if you're listening to this on your commute to the lab right now.
Right, why care?
If you are so tired of unrolling these reverse denoising trajectories just to get your model to follow a basic prompt, this paper basically proves you don't have to do it anymore.
You can just skip it.
Exactly. You can get state-of-the-art policy improvement purely on the forward noising process. And this is the crucial part. You keep your ultra-fast few-step inference completely intact.
Okay, we really need to unpack the mechanics of this because, a 4-step generator beating a 50-step generator sounds like total magic until you actually look into the weeds of the math.
Yeah, we have to ground this a bit.
Right, so let's start with the fundamental difference between traditional flow matching and MeanFlow. If you think about standard flow matching or, diffusion, it's essentially like driving a car, but you're only allowed to look at your speedometer.
That's a great way to put it.
You only know your instantaneous velocity, like your exact speed and your exact trajectory at that specific single millisecond.
Which mathematically means mapping out the entire route requires this constant, exhausting vigilance.
Right, you're constantly checking.
To get from pure noise all the way to your destination, which is like a clean, coherent image, you have to check that speedometer and adjust your steering over dozens or sometimes even hundreds of small sequential steps.
And every single one of those little adjustments requires a full forward pass, right?
Exactly. Every step is a full evaluation of a massive neural network.
And that is exactly why generation has traditionally been so incredibly slow. But MeanFlow, on the other hand, is just fundamentally different. It's like having a GPS that doesn't even bother with the speedometer.
It doesn't need to.
Right. It just looks at where you are, it looks at the final destination, and it just gives you the exact average speed and direction you need to get there over a set time interval.
It's a massive paradigm shift in how we think about these models.
Yeah.
Because instead of training a network to predict the conditional velocity at like a single isolated moment.
Instantaneous velocity.
Right. Instead of that, MeanFlow actually predicts the path integral of the velocity over a whole time block.
Oh, wow. So it's basically mapping out the entire displacement at once.
Precisely. And when you have that path integral calculated, you can take these huge, exact mathematical leaps. You basically just subtract the total distance from your current position, and you skip all those tiny intermediate steering adjustments.
Which explains why MeanFlow can generate high-quality images in just, like, a handful of steps.
Right. You're taking massive shortcuts that are mathematically guaranteed.
Okay, but getting the image out quickly is really only half the battle here. Because we also need these models to actually follow complex human instructions. We need RL alignment.
Which is usually the hardest part.
Exactly. And if you look at the field right now, if you don't use RL, models just tend to ignore the nuance in your prompts. But, and we've all seen this, when you try to apply naive RL, you get those famous reward hacking artifacts.
Oh yeah, the deep fried images.
Right. You know, the ones where the model realizes like, oh, the reward function really likes vibrant scenes. So it just starts spitting out these garish neon colored nightmares.
Or it scales an object up to bizarre, implausible sizes just because that triggers a higher CLIP score.
Yeah, exactly. It games the system. So preventing those artifacts requires really stable, high-quality reinforcement learning. And currently, I mean, the dominant recipe for that is something like GRPO group relative policy optimization.
But applying GRPO to diffusion models is computationally brutal. It's just so heavy.
Because you're forced to discretize the reverse generative process, right?
Yes. You need stochastic policies for GRPO, which means you have to inject randomness at every step, and then you have to calculate the exact probability of the specific path the model happened to choose.
Which essentially means every single step you take backward through that diffusion process, you are building this massive computational graph in PyTorch.
A huge one.
If you have 50 steps, you are storing 50 full neural network passes in memory just to calculate a single gradient update.
It's absurd. For a video model with billions of parameters, that requires an unthinkable amount of VRAM.
It's just an out-of-memory error waiting to happen. You can't run that on a normal cluster.
Yeah, you really can't.
So if GRPO is just way too expensive for most practical deployments, we obviously need an alternative. And this brings us to the second half of the paper's title, Diffusion NFT.
Right.
So can you explain the mechanism here? Like, how does forward process RL actually work in practice?
Well, Diffusion NFT, which, by the way, stands for Online Diffusion Reinforcement with Forward Process, it completely sidesteps that whole reverse rollout nightmare we just talked about.
Because it's likelihood-free.
Exactly. It's totally likelihood-free,
Yeah.
and it's solver-agnostic. It literally doesn't care about tracking the complex probabilities of individual reverse steps. Instead, it takes a batch of generated samples and just scores them using a standard reward model.
Okay, so it just generates a batch of images, and the reward model says, hey, this one's a 0.8, this one's a 0.2.
Precisely. Just a simple scalar reward. But the brilliance is what it does next. It takes those generated samples and splits them into two distinct groups, positive posteriors and negative posteriors.
So it's basically sorting the good from the bad.
Yeah, it's essentially a sorting mechanism. The high-scoring images form this target distribution that the model should actively move toward, and the low-scoring images form a penalty distribution that the model needs to avoid.
Okay, that makes sense.
And then Diffusion NFT forms what they call an implicit policy improvement direction. It folds those positive and negative signals directly into a standard flow-matching loss function.
Okay, so wait. If I'm understanding the physical intuition of this, you take an image, you add noise to it in the forward direction, and then you use the reward scores to either pull the model's predicted vector field toward that sample if it's a good one, or just push the vector field away from it if it's a bad one.
That's exactly it.
And all of this is happening entirely on the forward pass.
Entirely on the forward pass. You are doing online RL directly on the forward noising process. There's no reverse unrolling, no keeping 50 network evaluations in memory.
That is wild. Okay, so we have MeanFlow, which gives us blazingly fast generation because it uses this average velocity GPS approach. And we have Diffusion NFT, which gives us super cheap, stable RL alignment on the forward pass.
Right.
It seems so obvious, right? Like, just smash them together and you win. But this is where the paper gets incredibly interesting because, as they point out, you actually can't just plug one directly into the other.
No, absolutely not. There's a fundamental mathematical fatal flaw if you try that.
Right. There is this massive mismatch in the velocity space because Diffusion NFT is strictly built for the speedometer, right? It requires instantaneous velocities to mathematically calculate those positive and negative posteriors.
Exactly.
But MeanFlow, by definition, uses the GPS. It outputs average velocities.
And the authors actually walk through this total breakdown in Appendix B of the paper. It's really fascinating. Diffusion NFT's entire mathematical guarantee-like, the strict proof that the model is genuinely improving its policy, relies heavily on the fact that the optimized output is a marginal instantaneous velocity.
It has to be a posterior mean, basically.
It has to be.
Yeah.
So if you just naively grab the average velocity output from your MeanFlow model and shove it directly into the Diffusion NFT loss function, the math that actually decouples the positive and negative policies just completely falls apart.
You completely lose the policy improvement guarantee.
You lose all of it.
Because the loss function is sitting there expecting a specific velocity at a specific millisecond. And you are basically feeding it the average speed over the next hour.
Right. The optimization wouldn't have any idea what to do with that information. You would just be updating the network weights blindly at that point.
So they were stuck. The authors couldn't just throw out MeanFlow's efficiency, and they definitely couldn't sacrifice Diffusion NFT's stability.
They had to invent a mathematical bridge between these two very different velocity spaces.
And this brings us to the real theoretical breakthrough of the paper, which they call the Meanflow Identity. I honestly love this because it perfectly links the two concepts together.
It's a really elegant solution.
It is. The identity essentially proves that the exact speed you are going right now, your instantaneous velocity, is mathematically equal to your average speed for the whole trip plus an adjustment factor.
And that adjustment factor is key.
Right. It's the remaining time interval multiplied by how much your average speed is currently accelerating or decelerating.
Or, to put it in calculus terms, the total derivative of the average velocity with respect to time. And by using that exact physical relationship, the authors constructed what they call an induced instantaneous-velocity predictor.
Which is basically a translation layer.
Think of it exactly as a mathematical translation layer.
So they take their MeanFlow network, which outputs average velocity natively, and they just wrap it inside this identity formula.
Yes. And by doing this, the network's actual internal parameters, the weights, stay firmly rooted in average velocity space. It maintains all those properties that allow it to generate amazing videos in just 4 steps.
But during the training loop.
Exactly. During the training loop, the loss function sees the output only after it passes through that translation layer.
Oh, that's so clever. So the loss function literally thinks it's looking at a standard instantaneous velocity. It applies the diffusion NFT positive and negative rewards splitting perfectly, just like it wants to. But under the hood, the gradients are flowing backward through the identity and actually updating the weights of an average velocity model.
And the best part is, the authors didn't just run this code and get lucky. They rigorously proved that this mapping is a perfect one-to-one transfer.
Right, and theorem 3.4, I think?
Yes, theorem 3.4. In an idealized continuous time setting, if you optimize this induced predictor, the policy improvements map flawlessly back onto your average velocity generator. You get the ultra-fast generation, and you get the strict mathematical guarantee that your model is actually aligning with the reward.
Okay, I buy the idealized math. It's beautiful. But this is where I have to step in and play devil's advocate for the ML engineers listening who are probably trying to figure out how to actually build this.
Oh, the engineering reality is a whole different beast.
It really is, because if you look at that identity formula, the adjustment factor requires calculating the total derivative of the average velocity, and calculating a total derivative with respect to the input data involves a Jacobian vector product, or a JVP.
Which is notoriously awful to compute.
Awful. Like if I open PyTorch right now, load up a billion parameter video model, shard it across a cluster of GPUs using fully sharded data parallel FSDP, and then try to calculate a full JVP, my GPUs are genuinely going to catch fire.
Oh, they would instantly crash.
It requires all this complex cross-GPU communication that stalls training and causes instant memory blowouts. So how did they actually code this to run at scale without crashing everything?
That is the pivotal question, honestly.
Yeah.
And it transitions us directly into the practical implementation in Algorithm 1. This is where the paper evolves from, cool theoretical math into hardcore engineering reality.
Right, the actual code.
The authors were fully aware that a standard JVP calculation would completely kill FSDP training. So they introduced 3 major engineering hacks to bypass the compute bottleneck and prevent the training from collapsing.
Okay, let's go through them.
Hack number 1 is the finite difference derivative.
I love finite differences. Whenever the calculus gets too hard or too memory intensive, you just perturb the system and measure it.
Exactly. Instead of doing a costly exact Jacobian calculation, they just approximate the total derivative using a simple, central finite difference in time.
So they just take the time step, push it slightly forward, push it slightly backward, calculate the network outputs for both of those points, and then just divide by the time delta.
That's all it is. It is highly efficient. It avoids the massive memory overhead of a JVP, and crucially for engineers, it requires 0 complex cross-GPU communication.
Making it totally FSDP compatible out of the box.
Perfectly compatible.
Okay, so the finite difference saves us from the JVT memory explosion. That's huge. But wait, in the standard diffusion NFT objective, you're usually comparing a trainable live model against a frozen reference model, right? Like an exponential moving average, or EMA of the network.
Right, to keep things grounded.
So if you are perturbing the time step and calculating finite differences for both the live model and the reference model entirely independently, wouldn't their derivatives eventually completely desync?
You've hit on the exact reason for hack number 2. The paper actually calls that phenomenon reference drift.
Reference drift. It would be like, okay, imagine two ships trying to sail in a strict formation.
Okay, I like this.
The IMA keeps their starting coordinates close, sure, but if they're using slightly different compasses to calculate their immediate trajectory over a long enough time step, the gap between them just explodes. The formation completely collapses.
That is a perfect analogy. The EMA keeps the base predictions close together, but it does absolutely nothing to constrain the difference between their derivatives. And figure 8 in the paper shows this visually. If you calculate separate derivatives for the two models, the training loss just spikes wildly and the model collapses almost immediately.
Wow. So how do you actually sync the compasses?
You only use one compass.
Oh.
They compute the total derivative once using the frozen reference model. Just once. Then they share that exact same derivative term for both the trainable predictor and the reference predictor in the loss function.
Oh, that's incredibly elegant. Because the derivative is identical for both sides of the equation, the massive derivative difference term just cancels out entirely in the math.
Exactly. It stabilizes the training beautifully, and as a nice little bonus, it cuts the derivative compute cost right in half.
That's brilliant. Just freeze the derivative from the reference and force both models to use it. Okay, but there is one more piece to the derivative puzzle here. When you calculate that total derivative, you have to displace the samples along a specific vector direction.
Right. You need a direction to calculate the change.
And in the idealized math, you're supposed to use the network's own prediction of the instantaneous velocity as that direction. But what's the third hack?
Hack number 3 deals with exactly that problem. The conditional velocity direction. Calculating the network's own instantaneous velocity prediction requires a whole extra forward pass of the model.
Which is obviously expensive.
It's expensive, but honestly, worse than that, it severely destabilizes training.
Well, yeah, because if you use the network's own prediction as the direction for the derivative, you are basically calculating a derivative relative to a moving target.
Exactly. As the network updates its weights, the direction shifts, which changes the derivative, which updates the weights again. It creates this chaotic, uncontrollable feedback loop of errors.
Trying to anchor your optimization to a constantly shifting prediction just destabilizes the entire framework.
Which they actually demonstrate in Figure 9. So instead of doing an extra network pass to get a shifting target, the authors just reuse the forward process conditional velocity.
Which is just the ground truth velocity pointing straight toward the noise.
Exactly. It is a fixed north star. It's a model-free anchor that never ever shifts during training.
And I'm guessing you already have it.
Yes. You already have to calculate it for the standard flow matching process anyway, so it is entirely free to compute.
Okay, so to summarize the engineering reality here, because this is dense, they approximated the nasty JVP memory hog with a simple finite difference. Then they shared the reference derivative to keep the ship sailing in perfect formation and prevent that reference drift.
Yep.
They reused the free conditional velocity to act as a fixed north star for the direction. And finally, I assume, they wrapped the whole total derivative term in a stop gradient during optimization.
You bet they did.
Meaning they reap all the massive benefits of instantaneous velocity RL alignment, but they don't pay the massive compute tax. It's just pure efficiency.
It really is a masterclass in adapting idealized theoretical mathematical concepts into scalable distributed engineering.
So with all that math translated and the code highly optimized for FSDP, what actually happens when you unleash MeanFlowNFT on large-scale frontier models? Let's talk about the results, because the metrics here are honestly a bit absurd.
They really are. Let's start with images.
Right. On image generation, they applied this framework to Stable Diffusion 3.5 medium. MeanFlowNFT achieved the absolute best results on 6 out of 8 benchmark metrics compared to all the other few-step models out there, like DMD, CDM, AnyFlow, and RDM.
And look at the text rendering.
Yeah. I'm looking specifically at the OCR score, which basically measures how well the model can generate readable text on signs and stuff. The baseline RTDMD model only gets 0.30. MeanFlowNFT hits 0.65. It literally more than doubled the text rendering capability.
And you really have to look at the efficiency ratio to fully appreciate that jump in quality.
Well, right, because with only 4 sampling steps, MeanFlowNFT matches or outright exceeds the 40-step baseline diffusion NFT on major reward metrics like image reward and slip score.
It's getting the exact same alignment quality, but using 10 times fewer function evaluations at inference time.
It's insane. And the video results are where it truly flexes. As I mentioned at the top of the deep dive, they applied this to the WAN 2.1 1.3 billion parameter video model. A 4-step MeanFlow NFT has a VBench score of 84.33. That beats the 50-step Longcat Video RL baseline, which scored 82.57.
4 steps beating 50.
4 steps beating 50. It's incredible.
But the quantitative metrics only tell part of the story here.
Yeah.
If we connect this back to those reward hacking artifacts we discussed earlier, like the garish colors, the weirdly scaled objects, MeanFlow NFT, actually actively suppresses a lot of that.
Oh, really? How so?
Because it's doing likelihood-free alignment across the entire interval. Rather than making these discrete, noisy jumps, it produces much more faithful, visually coherent samples. The qualitative difference is obvious when you look at the paper's examples.
And I notice it scales really gracefully at test time, too, which they call step consistency.
Yes, step consistency is huge. Usually, if you tune a model specifically to generate an image in, say, 4 steps, and then you ask it to use 8 steps at inference, it just completely hallucinates.
Right. It just overfits to the 4-step discretization.
Exactly. But if you sweep the inference steps with MeanFlow NFT-like, generating a video at 2 steps, then 4, 8, 16, and up to 32, the output is incredibly consistent. The layout of the scene and the actual visual content don't wildly morph and shift around just because you gave the model more steps to compute.
Which is basically the ultimate proof that the RL actually worked the way it was theoretically supposed to. I mean, if the visual output stays structurally identical, whether you use 4 steps or 32 steps, it strongly indicates that the optimization genuinely improved the fundamental average velocity estimation over the entire flow map.
Right. It actually learned the continuous trajectory better, rather than just memorizing some specific time-step shortcut.
Okay, so what does this all mean for you? If you are an engineer building generative systems today, this paper gives you a literal blueprint to escape the alignment bottleneck.
A very practical blueprint.
You get the likelihood-free forward process RL stability of diffusion NFT. You combine it perfectly with the massive leap, few-step inference efficiency of MeanFlow. And thanks to their engineering hacks, it is highly stable for your large-scale FSDP training runs. You just don't have to choose between fast inference and stable RL alignment anymore. You can genuinely have both.
It's a huge win. And it raises a really important question for the entire field, and it's something I want you to really mull over as we wrap up today.
Yeah, what's the big takeaway?
As this forward process RL proves, it can outright beat multi-step reverse RL with 10 times fewer evaluations.
Yeah.
Are we witnessing the death of reverse process RL like traditional GRPO for diffusion models?
Oh, wow.
I mean, if flow maps and average velocity predictors can theoretically absorb any non-differentiable reward purely on the forward pass, without ever unrolling a costly reverse trajectory, perhaps the future of all generative model alignment is entirely likelihood-free.